So you were with a line integral. You're integrating some multivariable function, right? Multivariable functions graph as surfaces. In R3, right? And we were going to accumulate for only the points of that surface over some curve in the xy plane. And how do we define the curve? So how is the curve in the xy plane defined? What kind of thing defines that?
The vector function.
Good, a vector function, right? So it would be a vector function, and that will have two variables, right? X of t, y of t. So what is this? It's a single value vector valued function, right? A single value, single variable, vector valued function graphs as a curve in the xy plane. And we're going to integrate a multivariable real valued function over that curve. And what was the result of that? So what's the geometric result? So we're going to integrate, so we call the curve C. We're going to integrate over C. We're going to integrate f of xy ds. And what was the geometric result of that? What kind of geometric quantity did that give us?
We created a curtain from the line to the surface.
Okay, so it's the part, we want the part of the, yeah, we're going to only be looking at the points on the surface that are right above the line. So something like this. Okay, so we're only considering these z values over the curve, and that creates, he said, it creates a curtain kind of. Right. And what did the line integral calculate then?
The area of the curtain.
Right. So it's the area of that vertical surface that you get when you only take the points of your multivariable function, your surface, over the curve in question. So it gives the area of the vertical curtain. Like a wave, it could be a wavy, some kind of wave. It could be wavy. It doesn't have to be wavy. It could be planar. You saw the example where there was planar, but whatever's hanging straight down from those points onto the curve, it's going to be that area of that surface. And how did we solve it? What did we do to solve the line integral? What was the process of being able to solve this?
You needed to find parametric equations.
All right, so so we have our vector function r of t. So our vector function gives us the equation of the curve. And we're integrating the surface or the multivariable function over that curve. And so what did that consist of? How are we able to solve this, right? Because this involves two variables, right? This involves x and y. ds was our little part, right? ds was little bits of the curve. So what was the process to solve that?
Whereas the variables in terms of t.
Right. So we have a single. We still have a single integral. So we need to get it in terms of a single variable. That's going to be t. So we're going to rewrite our function using. We only care about the ordered pairs along this, right? Along our curve. So we can just consider the function along that thing. And then what was ds? Remember what ds was?
Absolute value of r prime t.
Yep, and we showed where that came from, right? So We know that ds dt what is that? That's a little change in the curve for a change in time. So it's kind of like speed, right? That's like speed. It's like how far you go per change in time. It's like speed. Well, speed is the what magnitude of velocity. So speed is the magnitude of velocity, and we can use that to rewrite ds as r prime of t magnitude dt. So this is how we solve those. And when you solve that, again, you got the value of the area of this kind of vertical surface, whatever it was. It could be wavy, it could be flat, because that's just in a nutshell what you did for Friday. Any questions on that? Okay, so this is actually line integral type 1. So line integral type 1 is the line integral of a multivariable real valued function. So there's another kind of line integral. That's what we're going to do today. Type 2. Line integral type 2 is a line integral of a vector field. Okay, so let's take a look at that. Any questions before I erase this? So that's just an overview of what you did on Friday. Okay. So the next kind of line integral is a line integral of a vector field. So now, rather than considering a surface over a line, we're going to consider a line. So still like a curve C here, but rather than underneath or for a multivariable function surface, we're going to consider that C through a vector field like this. Okay, so this is starting with T1. So our path C is still a multivariable function. Okay, so it's still so we still have a vector function that gives us our curve, right? Vector function gives us a curve in R2. But now, rather than integrating a multivariable real valued function, we're gonna integrate a vector field. So to develop what's going on here, it's really helpful to look at a really common application of this, where the vector field F is a force field. So what is the general form of a two-dimensional vector field? What kind of function is a two-dimensional vector field? So remember we said this course is like a survey of all different kinds of functions, so we want to keep them all straight. So if I want a two-dimensional vector field, what does that look like in formula, in the form of a formula?
It's x of t and y of t.
Okay, so are you saying it's like this?
Yeah.
That gives a curve, right? That gives a curve, so that doesn't give a vector field. Remember, what goes in and what comes out when you're forming a vector field? Like, what's the independent thing?
It's a point, and then it yields a vector.
Right.
So you have two independent functions.
Okay. So what is the independent thing in a vector field?
XY. Position.
Position, right? So for an R2, it's going to be position, right? And what gets spit out then?
A vector.
A vector. Each component could be a function of position, right? So your x component is a function of position. Your y component of the vector is a function of position. So what's that? That's a multivariable vector valued function. Those give vector fields, right? Multivariable stands for location, and then it spits out a vector, so a vector valued function. All right, so we're gonna be integrating. So if this is a force field, and we think about an object moving along the path. Let's think of maybe a car driving on this road. Okay, so there's a car driving on the road, and there's a force field that's applying force to the car according to the position, right? So at any position of the car along the road, this will tell us the force. And so the most common thing would be like the wind, all right? So this is a wind field, and the car, this is the force of the wind on the car at any point along the road. And so what this line integral of this wind field would be how much work the field or the wind is doing on the car as the car drives this path. Okay? So as we know in a car, the wind can blow in all different directions, but in the car, we force the car to stay on the path of the road. But as we're doing that, the wind is applying force to the car as we move, and so the wind is actually doing work on the car. And so this line integral is going to be the total amount of work that the wind does on the car, say as it travels the road. So this is complicated because the road turns, and as soon as you move along the road, the vector of the wind it's continually changing, right? The vector applied to the car, the wind vector applied to the car changes for every little change in the car's position. Okay, so how are we going to do this? We need the accumulation or the total work that the field is doing on the car. So what was our formula for work again? Just our generic formula. Force times distance, right? But then in this class, we said, how do we calculate work in this class when we have maybe a changing force?
You can use the dot product.
Right, remember? It was the dot product of the force and the distance vector, right? Because we wanted the dot product was the amount of force only as much as in the direction of D. So remember the girl pulling the wagon. So if this is the displacement vector, and when you pull a wagon, you don't pull horizontally, you kind of pull up a little bit, but we only want as much of the force as is in the direction of D. So that's why we do F dot D, because F dot D is the product of the magnitudes, but only as much as the force is in the direction of D, or cosine theta. So we want to use the same principle here, but we need to accumulate lots of little bits of work all along the way. Okay, so right here at this point, the force looks about like, if I pull off this one right here, the force looks about like this. So say this is at some t value right here, and so this would be f of t. Sorry, this would be f of x comma y. So it'd be xt yt. Okay, but what do we want? We only want the amount of the force, that's in the direction of that we're going. Right? But as soon as we move a little bit, so if this is r, so what about the direction that we're going? What does that have to do with? How am I going to get the direction that we're going, say, at time t?
Take the unit vector of the RT.
So does RT give me that? Is RT in this direction? Here's the origin down here.
Is it r prime of t?
Yeah, so the origin's down here. What is RT? RT is like a position vector that points at my location, right? So if this is 0, 0, RT would be this vector here, from here to there. That's RT, right? It's giving me position of the car at time t. So in standard position, you put the tail at the origin, and then its tip would be at our location. So instead, we need, what's the direction of this right here? Someone said it?
R prime.
We need r prime of t, right? So r prime of t is, how do we find r prime of t? That was, we found that by? It'd be our x component, dx dt, dy dt. Another way we could write that let's see here. Okay, so what do we need? So we need what? We need a little change in position, right? So we're doing f dot d. So d is like a little change in position, and we need it in this direction. So what would that vector be? We don't want dx dt, dy dt. We just want a little change in position. So that would be just dx dy, right? So dx dy then is the same direction, but it's representing a little change in position, like a little ds, like we saw before. So we need an infinitesimal a vector in the direction of the velocity, and that could be dx dt, and that's really just our differential of the vector function. That's dr. Because this is dr dt, right? This is dr dt. So now I have my little displacement vector, and I have my force vector there. So what's the little amount of work that I'm going to get at that point? So the little amount of work I'll get at that point is I want to take as much of the force as is in the direction of motion. So my little bit of work is going to be f dot dr. Just like we said, f dot d. But now that d has to be just a little change in position, because as soon as we move to the next point, we have a different force and a different direction that we're going. Okay, so now I'm going to accumulate, so the total work I want to accumulate all these little bits of work along the path of C. Okay, so how are we going to solve that then? So what is dr? We said dr is dx dy. So that's going to be so if dr dt is dx dt dy dt, then dr is going to be dx dt dy dt times dt. Right? So I can just, to solve for dr here, I can just multiply up dt. And so my dr is going to be what? I'm going to take my vector function and take individual derivatives, and then times dt, and I'm going to write my vector field f in terms of t, just like you did for the other line integral problems. So we're going to rewrite f in terms of t. To get this dr part, we're going to do the derivative vector function and multiply by t, and then this whole thing will be in terms of t. So it doesn't have to be work, but I think work is the easiest way to develop this, thinking about this as a force field, and this is an object moving along a path in that force field. And so what is this? The total work that the field does on the object. And it's just summing up a bunch of F dot D's, right? So summing up a bunch of little amounts of work to get the total work, the work that the field is doing on the object. So if from T1 to T2, this is the direction of my path, we could kind of make a prediction here. Will the total amount of work be positive, close to 0, or negative? So here's the car moving along in this wind field here. Will the wind, overall, will the wind do a positive amount of work on the car? In other words, will it help the car along? Or will it do a negative amount of work on the...
It'll be positive.
Okay, so noticing that the components of the vectors in the direction of the curve are going in the same direction as the curve, right? So if you think of components of these vectors, they're kind of pointing in the direction of the curve all through here. Now through here, the curve is going like orthogonal to the vector field. So through here, there's kind of a zero-ish work, right? The wind is blowing right across, like laterally on the car. So then in terms of the car's motion, the field is doing no work on the car through there, or very little. But then as we turn back up this way, now the field is doing positive work on the car again, because the vectors are pointing generally in the same direction as the car's motion. So this particular line integral from T1 to T2 of this vector field, we would get a positive result because it's strongly positive here, then kind of zero-ish, then positive again at the end. Okay, so I did a lot of talking. So anybody have a question? Was this clear, or is there anything I need to clarify here? So the idea of the line integral of a vector field. A very prevalent example of that is that it's the total work that the field does on an object moving through the field. Okay, let's look at another just visual example, and then we'll do an actual. We'll do a couple like computing examples. So this one. So this is the path R of t equals 2 cosine t, 3 sine t minus 2. That's the path. And t is going from 0 to 2. Actually, I want to go from 2 to 0. So t is going to go from 2 to 0. So this is actually t equals 2. And this is t equals 0. How does that make sense? T equals 0. Negative. Negative 2. I don't know why that's the case. Why is it showing t equals 0 here? Because that would be negative 2. Oh no, t equals 0 is positive 2, right? Okay, so yeah, t equals 0, it's not negative 2, positive 2. All right, I'm back. I'm understanding it. All right, so this is the path. 2 cosine t, 3 sine t minus 2 as t goes from 2 to 0. So t equals 2 is here, and 0 is here. And then the vector field is sine y1. Okay, is this a gradient field? Sine y1. Let's check. So if it's a gradient field, then we're saying that this might be what? The partial derivative with respect to x for some function. And this is the partial derivative of y for that same function. So if the partial derivative with respect to x is sine y, then what perspectives does that give us on f? That tells us that f is what?
X sine y.
X sine y plus possibly some what?
Some function that contains y.
Just y, because that would go to 0, plus a constant, right? So from the perspective of sine y is the partial derivative with respect to x, we're looking at x sine y plus gy plus c. If the partial with respect to y is 1, then what perspective does that give us on the function? Well, then we'd have a y plus some function just of x plus c. And the question is it possible for these two to be the same function? Can we write one function f that matches both of these perfectly?
Absolutely not.
He says no. So this is okay, right? We can say that that y is this g of y. And h of x, we don't really have a function of x, that's okay. But what about this? That would have to show up, that has to be in both, right? It has to be here and here. Well, there's nothing down here that allows me to have x sine y. So this is preventing, this x sine y prevents this from being a gradient field because there's no way. So down here we'd have to have x sine y in order for this to work. So these are not the same. And then the conclusion is you can't write a potential function. You can't write, it does not exist. There's no function whose partial derivative with respect to x is sine y and whose partial derivative with respect to y is 1. It's impossible. Therefore, what can we say about the vector field?
It is not a gradient field.
Not a gradient field. So that should be familiar. That was also from work you did on Friday. That's another example. Okay, so, but we can still do it, even though it's not a gradient field. It doesn't affect us being able to write, compute a line integral or write a line integral of a gradient field. That's okay. You can do line integrals through gradient fields or non-gradient fields. Okay, perfectly fine. So, as as we go from 2 to 0, so I want to do the line integral from 2 to 0 of f dot dr. I just want to predict, is that going to be greater than 0, less than 0, or close to 0? Because I'm going this way. I want to go this way on the curve. So looking at the beginning here for this first part here, do we have, is this going to give a positive or negative or 0 contribution to the line integral, starting from, say, here to here?
Positive.
Positive. Vectors are pointing generally in the direction of the curve. So we're going to positive. What about through this part here?
About 0.
0-ish, right? So the direction of the vectors is primarily like perpendicular to the curve, so there's going to be no contribution in a dot product of those vectors to the curve. And then what about this down here?
Negative.
Negative, right? The vectors are pointing in the opposite direction generally. There's components of the vectors pointing in the opposite direction of the curve. So we had a little bit of positive, then we had a 0-ish part, and then we had a negative part. So what's your prediction for the overall value? Positive, negative, or 0?
I think negative.
So yes, so it's like positive, so greater than 0 from here to here, kind of really close to 0 through here, and then less than 0 for the rest. So does it look like the positive contribution is less than the negative contribution? You got a longer span here of where the vectors are pointing against the direction of motion. So that would indicate that this is going to be less than 0. Okay, so that's just an example of the visual. Well, we're going to get to computing them in a moment here. Any questions? So, a little bit of positive, 0-ish, more negative. So the overall result of that line integral, that line integral will come out to be negative. Okay, let's do a different path, and we're actually going to compute the line integral for a different path here. Unless there's any questions. All right, now I want to do the path along the parabola, starting at negative 1, 1, and then ending at, so it's going to go through here, and then it's going to go through what? 2, 4, way up here. So I want to calculate the line integral. So I want to calculate f dot dr, the line integral of the vector field, along y equals x squared from negative 1, 1 to 2, 4. So first let's predict whether we think that's going to be a negative or positive result. Okay, starting here. What do we got? It's kind of 0-ish, maybe a little bit negative through here, 0 here, and then what do we got going on here? It's the contribution, pretty strongly positive for a lot of the way here. So what do we predict for the value of this line integral? So just a little bit negative, mostly 0, and then pretty significant positive to the end.
Greater than 0.
Yeah, so we're going to predict that this is greater than 0, but we want to actually get the value now. We actually want to calculate this line integral of this vector field and show that it is greater than 0. So what do we need to set up a line integral of a vector field? We basically need two things. What do we need? What are the two components, the two types of functions that we need to do the line integral of a vector field?
F of dr?
So yeah, we need the field, which we have. It's the sine y1. And then we need what? We need to parameterize the path. We need the path. Right? Those are the two things involved here. We've got a path. That's a function. It's a vector function. Vector functions give curves. All right? And then we need the vector field. Right? And we've got that. That's our multivariable vector valued function. That's the vector field. So I need to write, so back earlier in the course, when we started talking about vector valued functions, we were writing their equations. We did lots of this. So now I've got the equation, I've got the curve y equals x squared, and I need to write it as a vector function. Remember how to do this?
You set one variable equal to t.
One of the techniques we had for this was setting a variable equal to t, and then the other variable, we can simply use the function that we're given. So which variable do we want to make t?
X.
Make xt. And then what will y be?
t squared.
So hopefully that's at least familiar, right? So in the non-circular, the non-elliptical functions, if we just had a y as a function of x, you could just make your independent variable t, and then your dependent variable follows the same formula that the curve was given as, right? So x and x squared, right? This is y equals x squared. All right, so here we go. So we're computing f dot dr. And so what's my f? I need to rewrite my f in terms of t. So what would f be?
Sine t squared.
Sine of t squared, right? Because we only care about values of y on our vector functions. So it would be sine of t squared, comma, 1. All right, dot what? What is dr? We said dr was x prime dx dt, y prime dy dt, dt. So what's x prime of t?
Just one.
1.
2t.
And then 2t.
2t dt, which will then give me the, and then t goes from what to what? So my t is the same as my x coordinate, right? So the t value here is the same as my x coordinate, so t is -1, and then we're going to finish up at t equals 2, because t is the same as the x coordinate. So -1 to 2. So we're going to have -1 to 2 of sine of t squared times 1 plus 2t times 1 dt. Okay? Sine of t squared does not have a closed form antiderivative, so I'm going to use my software to solve this, right? So now we have a single variable integral, and normally you've been solving these for three, 4 semesters now. For this particular one, sine of t squared times 1, well, that doesn't have a quick and easy, I think it doesn't even have a closed form antiderivative, but it doesn't mean that that doesn't exist. It's just that we need technology to do a numerical value for us to solve it. So here we go. So do Control-Shift-I. So we're going from -1 to 2. And we're expecting the value of this to be what?
Greater than 0.
Yeah. So sine of t squared. I'll just do x squared. It's fine. No, just sine of t squared. What, plus 2t? Is that right? And then this is dt. And sure enough, positive 4.11 something. Greater than 0, what we predicted. Questions on setting up the line integral of the vector field? You're going to rewrite f in terms of t, and then your dr is going to be your derivative function of the path, dt. Okay, what time are we out of here? Time's class 11:35? Yeah, 11:35. Okay, so we got 10 more minutes. Any questions on this example? Okay, let's do another example. All right, so here is the vector field. Small here. Let's see, the vector is a little bit bigger, so there we go. All right, I think that's good right there. All right, so this is the vector field xy and 1 minus x, and we want to find the line integral of the vector field along the counterclockwise path of the circle of radius 2. From 2, 0 to negative 2, 0. So basically what I'm saying is here is going to start at 2, 0, and we're going to have the path, this 2 is about up here, so we're going to have the path from 2, 0 to negative 2, 0. Okay, and so what do we need? What do we need to do this line integral? We need two functions. What two functions do we need to compute this line integral?
F and dr.
Okay, so not dr, we want to, yeah, but we're really interested in r, right? We're interested in the path of c. We're going to use that path of c then to compute the line integral. We're going to get the dr from that. Okay, so we've got our f. F was given as xy and 1 minus x. Right? That's our multivariable vector valued function, gives a vector field, right? That's what you see in pink there, purple. And then what is my r going to be? So what is it? It's the counterclockwise path from 2, 0 to negative 2, 0 along the circle of radius 2. So I'm going to make x equal to t. Is that right?
Wouldn't we need a trig function?
Okay, so remember, we always want to use the most natural parameterization. And so again, back in the third, fourth week of the course, we worked hard on these, writing vector functions. Do you remember? So if you want the top half of a circle of radius 2, what's the natural way to write that as a parameterized curve?
You would use cosine squared and sine squared.
Okay, cosine, so I have cosine squared and sine squared being offered up. Agree with that?
You need the 2 in front.
2 in front. So 2 cosine squared, 2 sine squared. Do we have an agreement on that?
Wait, actually, I don't think it'd be squared. It'd just be 2 cosine of t and 2 sine of t.
He's changing his mind. What about the rest of you? What about the rest of you?
I don't think it's correct, but I'm just thinking the simple x squared plus y squared equals the radius squared.
So you don't want to use cosine and sine?
No, I was going to use
Not to begin with. Maybe if I see a correlation, once I go down in the problem, I'll change everything. Because if you change this to cosine and sine, won't you have to change the f function to cosine and sine?
I always want to use the natural parameterization for things. What if, so the problem comes, maybe it would work, maybe it would work to do what, t and what, square root of?
4 minus x squared, or t squared.
Okay, So first of all, this is not the natural way to do a circle, but the problem comes when, what if we were to go like three quarters of the way around, or all the way around? Then what? Would this be right?
No, it wouldn't.
Yeah. So the natural parameterizations of circles and ellipses use what, right? So this, we definitely talked about this and did lots of examples and worked on this. When you have functions that are based on circles and ellipses, when we're going to parameterize those in a vector function, we don't want to do this. It's not natural. The natural way is to keep it as a function that's going to work no matter what the t range is to use cosine and sine. Now the question is it 2 cosine squared, 2 sine squared, or not? Okay, hopefully you're thinking, you're being quiet, but hopefully you're thinking that's just cosine and sine, right? The very definition of cosine, if you didn't know this, today's the day. You know it forever. The very definition of cosine is the x-coordinate on a circle. That's the definition of it. It's the x-coordinate on the unit circle centered at the origin. And the very definition of sine is the y-coordinate. So when we're using sine and cosine to write x and y coordinate, then we just can use x and y. Now it's radius 2, so we had to scale it up by 2. So cosine t is the x-coordinate on the unit circle. Sine t is the y-coordinate on the unit circle. Never forget that. Never forget that. That's the basis of sine and cosine. Coordinates on the circle. That's what they give. All right, so here we go. So we're going to set it up now. We need our dr. So dr is negative 2 sine t and 2 cosine t dt. So we're going to rewrite our f dot dr then as, oh, what do we predict for this one? So we're going against the grain here. So negative, just very small vectors, so it doesn't really matter the direction, but 0, and then kind of a 0-ish, and then negative again at the end. So negative at the beginning, all through here, 0-ish in the middle, 0-ish through there, and then negative at the end. So we're predicting this will be negative. So f is going to be what, 2 cosine t, 2 sine t, 1 minus 2 cosine t. So I'm just rewriting the vector function using the x and y. We only care about the x and y ordered pairs on this curve. So this is our x and this is our y on the curve. So x times y, 1 minus x, dot dr, which was our negative 2 sine t, 2 cosine t, dt. And this is going to be the integral from what to what? T goes from what to what?
Since it's a circular path, it will be 0 to 2.
Okay,
Or
so t is our...
We don't have it in terms of radians, so never mind. It will be...
Nearby.
Yeah, it'll be 0 to pi, right? That t is taking on... The parameter here is taking on... Or the t is taking on angle measure. And the angle measure we need from the right side of the circle up top to the left side would be 0 to pi. Don't have time to solve that. But we know, looking at the picture, that it should be what?
Negative.
Negative. So we're going to do the dot product. 2 cosine t, 2 sine t times that, plus 1 minus 2 cosine t times that. That's a long and not difficult, but kind of tedious Calc 2 trig integral that you have to work your way through. And we're expecting that thing to be less than 0. But visually, right? Negative through here, 0 all the way through here about, and then negative, a little more negative at the end. Questions on setting up this line integral? So to solve it, you do the dot product. Means multiply and add. And then you'd have kind of a little work to do a trig integral like from Calc 2.